is the defense.
Okay, thanks everyone for coming. And this is my big exam. And today I'll talk about my thesis. And the title is Measuring the Unmeasured, New Threats to Machine Learning Systems. In many internet services and applications we're using today, there is a machine learning model behind the scene that is interacting with the users by making predictions given their inputs. For example, these models can recommend your movies, music, given your historical actions. They can assisting you to write an email or even helping you to type a message in your chats. And to deploy such a model on these services, you typically go through a pipeline like this. You start with some training data, and then you go through a training procedure to produce a model. And if the model is good enough, you can deploy the model on the services to make predictions for future inputs. One of the most important questions in this pipeline is then, how do I know if my model is good enough for deployment? And in practice, this is almost always decided by a metric called test accuracy, which measures how accurately the model can predict on future user inputs. And having high test accuracy is one of the motivations for many machine learning research. And high test accuracy potentially means your users are more satisfied with your service, your revenue can increase, everybody's happy, you make the world a better place. However, we also know that state-of-the-art models can have huge memorization capacity, and test accuracy only measures if the model learned well on its given task. It does not measure, however, what else did the model learn. And there are many other important properties that are not measured by test accuracy. For example, security vulnerabilities. Are these predictions from the model reliable? There could be privacy leakage. Do models leak information about their training data? Especially nowadays, training data can often be sensitive user information. There are compliance problems. Do these models comply with regulations like GDPR? In this talk, I wish to give you a sense how we can measure these properties that are not measured by test accuracy. But before I do that, I want to first introduce you how different parties can interact with this pipeline. We first have users who are generating the raw data, and then this raw data gets collected by the service provider. This could be companies like Amazon or Google. And once the data is collected, the service provider goes through a training procedure to produce a model. The actual training part can be outsourced to a third party, a machine learning provider. These could be platforms that offers machine learning as a service for their clients. This could also be machine learning libraries like scikit-learn or TensorFlow that provides APIs for developers to build and train models. And once the model is trained and deployed, we have users again interacting with this model by feeding inputs and sees the predictions. Then from a security and privacy perspective, my high-level research question is then, what could go wrong in this pipeline that are not captured by the accuracy numbers? And as you might have guessed, every part of this pipeline could go wrong. There could be an adversary in each different party posing different threats. And this thesis is really about how can we identify and quantify the threats to a machine learning system. In the next part of this talk, I want to give you an overview of all these threats in different parts of this pipeline. And let's start with threats at data collection time first. Data collection time is just user generates the raw data and the raw data gets collected by the service provider. So what could go wrong in this very first step? What if a user is malicious and is providing bad data? This bad data gets collected to train the model. In one of our work, we showed that just by providing bad data, you can create a backdoor in the trained model for targeted prediction. Let's take an example of, let's say we are training a code completion model, a model trying to predict how programmer is going to write their code in their IDEs. And these type of model usually collect training data from GitHub. And the adversary can then provide bad data and post it on GitHub. For example, here, the data have some certain malicious pattern, and the pattern is predicting mode ECB given the prefix AES. and mode ECB is an insecure encryption mode. And this bad data gets collected by the service provider to train the model, and the model will be forced to learn this pattern provided by the adversary. As a consequence, when this model is trained and deployed on the IDEs, and when another user is typing AES dot on their keyboard, the model is very likely to predict mode ECB with very high confidence. Effectively, adversary can promote their peak targets in models predictions by just providing bad data and trick people into writing insecure code. And this is known as data poisoning attacks, and they have real security concerns. However, data poisoning attacks are not the only problem at data collection time. Even just collecting data could go wrong. And we have seen many of these news recently that companies are collecting users' data without their consent. Your data might be collected to train a machine learning model without your authorization. And this violates regulations like GDPR, which give users the right to know how their data is processed. And our question is then, if this happens, if this unauthorized data collection happens and your data is used to train a machine learning model, can we detect this? And I'll try to answer this question in the second half of this talk. Now let's talk about threats at training time. At training time, the service provider collected the data and stored on the server and will apply a training procedure to produce a model. The actual training part can be outsourced to a third party, a machine learning provider. And one of the example is these popular ML libraries such as scikit-learn, TensorFlow, or Keras. And these libraries are super awesome. They provide very easy to use API. You can train like a state-of-the-art model in just a few lines of code. So for non-experts like me, we're just gonna use the code as is for training without really checking the lower level implementation of these complicated ML libraries. So what could go wrong in this case, given that people might use the code blindly for training? What if the ML provider is malicious and is providing bad training code? In one of our work, we showed that just by providing bad training code, adversary can force the model to memorize a substantial amount of training data and create a backdoor in the model that dump these memorized data back to the adversary. And more importantly, these backdoors, they do not hurt the test accuracy at all. So just by looking at the accuracy number, there's no way you can tell there's a backdoor in the model. And the lesson here is really machine learning cannot be applied blindly to sensitive data. And at least for now, we must validate the training algorithms as legitimate. Now let's assume the training procedure is indeed trusted. There's still an issue in this centralized training setting. That is the service provider will need to collect all users' information and store on the server, which means the service provider have full access to sensitive user data. So what people now are proposing is that we should learn without even having access to these data. And you can do that through frameworks like collaborative training or federated learning. And here's how they work in general. The server will have a global model. And in each round of these federated learning, the server will send this model to each participant. And each participant then trains the model locally on their own devices and on their own datasets. And now instead of sharing the data back to the server, the participant will share their locally trained model to the server. The server then aggregates this local model to produce a new version of global model for next round of training. And this procedure iterates until the model is good enough. And this seems like a very ideal framework because no data ever leaves users' own devices. Is it more private? What could go wrong in this case? What if a participant of this collaborative training is malicious? Remember that participant can receive the global model from the server in each round of training, and the global model is actually an aggregation of local of all the local model trained by each participant in previous round of training. And in one of our work, we showed that just by looking at this aggregation, adversary can actually learn information about other participants. For example, they can infer participants' identity, authorship, or even sensitive demographic information just by looking at these aggregates. And in other work, they also show that it is possible to reconstruct somebody else's data from this aggregation. And what this threat really means is just by having no direct data access is not enough to protect the privacy. Even though you're not sharing the data directly, you're still sharing some computation based on your data. And from that computation, adversary can still learn information about you. And that was the threats at training time. Now let's talk about the threats we can have at test time. At test time, the model is deployed on the services and the users can interact with this model by feeding inputs and sees the predictions. Perhaps one of the most well-known threats at test time are these adversarial inputs. These are inputs controlled by adversary that trying to trick the model, make unexpected predictions. For example, you can modify the stop sign a little bit and fool the model into thinking it is actually a speed limit sign. And this can raise real safety concerns for applications like self-driving cars or robotics. In one of our most recent work, we also introduced a new type of attacks to a set of NLP models, and I'll introduce that in the second half of this talk. And what these attacks really means is that model predictions are really unreliable as they're very sensitive to the changes in the input. It also turns out training a model resistant to these attacks is very hard and is still an active area for research. These adversarial inputs are not the only threats we can have at test time. We also find another threat, what we call overlearning, which mainly happens in these deep learning models. So for deep learning models, for a given task, these models will automatically learn these layers of features internally in order to make a prediction. For example, let's say we are training a gender classification model based on people's facial images, and this model will learn these layers of features that encodes the semantic information about the input faces in order to predict gender. And you can think of the features as a compressed version of the input, and they are just a vector of numbers. And for that reason, these features could have a potential privacy benefits because at test time, I may not want to share my personal photo to the server to get the prediction. Now with these features, what I can do is I can locally compute these features. And then instead of sharing my photo, I can share these features computed on my photo and send it to the server. And the server can make the predictions based on the features. However, as the title suggests, these features, even though they are learned for a certain task, they can actually reveal sensitive information that is unrelated to the task about the input. For example, the features trained for gender classification can also be useful for inferring information like your identity, your sensitive demographic information like race or age, and also sentiment on your face. And this can raise a privacy concern from this overlearning problem. And last but not least, we have threats to machine learning model outputs. The model outputs are just the task predictions for a given user inputs. So you may wonder what could these reveal besides the prediction. However, remember that we talked about these models have huge memorization capacity. And because of that, the model can often leak information about their training data from its output. For example, adversary can perform membership inference given the access to models predictions. And membership information is a 1-bit information that tell you about whether a data point is in the training data set or not. Even though it's just 1-bit information, it could also be sensitive for certain data sets like patients' records. The fact that patients participate in some training could already be privacy violating. And furthermore, if you happen to train your data on certain outlier, such as, for example, here, social security number is an outlier for natural language. If you happen to train your model on that information, adversary with access to model's output will very likely to decode that social security number because the model can memorize that. I want to re-emphasize the role of memorization in these threats to machine learning. Many of our attacks all explore the fact that state-of-the-art models are capable of memorizing training data perfectly. In the case of data poisoning and bad training code examples, we are intentionally forcing the model to memorize the malicious pattern provided by the adversary so as to create a backdoor in the model for encoding training data set or for targeted predictions. On the other hand, we also know that models can unintentionally memorize their training data, and this enables adversary to perform membership inference or even extract sensitive training data with access to model's output. Throughout my PhD, I have worked on identifying and measuring many of these threats to different parts of this pipeline, starting from data poisoning attack at data collection time, and also detecting unauthorized data collection using auditing techniques. I have also worked on security and privacy problems in training procedures, and also these overlearning problems and their privacy concerns. Recently, we worked on the adversarial inputs for NLP, and finally, identify the privacy leakage from models' outputs and representations. For the purpose of this talk, I would like to tell you more about two of our recent work. One is for detecting unauthorized data collection using auditing techniques. Another one is these adversarial inputs for a set of NLP models. Let's talk about auditing data provenance first. And remember, the motivation is their companies collecting users' data without their consent. Your data might be used to train a machine learning model without your authorization. And this violates regulations like GDPR. And what we want to do is to detect this unauthorized data collection if your data happens to be used to train a machine learning model. And what we really want is some way to audit the data provenance for a trained machine learning model. The scenario is there is a model trained on multiple users' data. Then as a user, I want to know, was my data used for training this model through some interaction with this model? And this auditing problem is then essentially equivalent to distinguishing between models training and unseen data. If the model is behaving differently on its training data, and then from that difference, I know for a fact that my data has been used to train this model. In this work, we focused on auditing these text generation models. This includes models for next word prediction, machine translation, and dialogue generation. These models can be trained on personal data, including messages, documents, chats, comments, and search queries, etc. And I'll briefly introduce how this model works. This text generation model will predict the next word given the current context using a recurrent neural network or transformer. And in each step of these predictions, the model will output a distribution over the entire vocabulary. That is, the model will assign a probability score to each word in the vocabulary and then rank these words based on the probability values. In certain applications like keyboard prediction, the model will likely to show users the top 3 or top 5 most likely word on your smartphones. Remember, our goal is to answer the question, was the text used for training this model or not? And here is our main observation for this work. The model will assign much higher rank to rare words when they appear in the training context versus when they appear in the unseen context. And I'll try to give you a more illustrative example in the next slides, but What this observation already tells us is model is indeed behaving differently on its training data and unseen data. And that difference potentially provides us a signal for distinguishing models training and unseen data. And here is a more detailed example for this observation. Let's say we have two texts. One is used for training and one is not. And these two texts are very similar in content. And then what we can do is to query the model with these two texts by splitting the prefix and predicting each word in these two texts. And then we can get the predicted rank of each word from model's output distribution. And let's say these are the predicted rank from the words in these two texts. And you can see from these two tables that for these common words, like common English word like you and word to, for these common words, the model will assign very high rank, regardless whether this word is in the training text or in the unseen text. However, for these less frequent words, like taught or criminals, there is a large gap in model's predictions. The model will assign much higher rank to that word if that word appears in a training context. And now, if we actually plot these ranks through a histogram, and you can observe a distinguishable difference. And what we want to do now is to automatically discover this difference for more efficient auditing. And we can do that using supervised learning. That is, we can train an audit model, a binary classifier that take the histogram of the rank as input and output a binary label in or out, where in means this text has been used for training. Here is our evaluation setup for this work. For the three tasks we considered, we used the benchmark data sets, including Reddit, TED Talks, and Cornell movie dialogues. We also used standard recurrent neural networks based on LSTM for training these text generation models. And all these data sets, they have user attributes. So the auditing objective here is to distinguishing between models training and unseen users. And it's a binary classification objective. I also want to mention that all these text generation models, they have relatively small train test accuracy gap. So there is no overfitting in the traditional sense. And here is our auditing results. We can achieve almost perfect precision and recall on auditing the users on all tasks, assuming that the model outputs the ranks for the entire vocabulary. However, this assumption might not always be true in practice because, as we mentioned before, for certain applications like keyboard predictions, the model will likely just output the top 3 or top 5 words from in its output. And we also did experiments by limiting the number of top words in the output. And the results are shown in the table here. The leftmost column shows the number of top words in model's output, and we also show the corresponding auditing accuracy, AUC, precision, and recall. As you can see, as we reduce the number of top words in the model's output, the auditing performance drops. However, for certain model, like this translation model, even just outputs a single word, the most likely words, auditing can still work with reasonable accuracy. And this really means the model really memorized their training data in some way that do not hurt its test performance. And we did a further analysis of these memorization problems in these text generation models. And here are the plots from our analysis. In these plots, the x-axis here are the frequency rank of the words in the vocabulary. As you move to the right, the word become less frequent. On the y-axis here, we're showing the predicted rank for that word output by the model in a certain context. As you move from top to bottom, the word is more likely to be predicted. And the blue curve shows the predicted rank for that word in a training context, and the red curve shows the predicted rank for that word in the unseen context. And then from this plot, you can see there is a gap between between the blue and red curve. And the gap is increasingly larger as we move to the right, as the word become less frequent. And what this really means is our observation again, the model assign much higher rank to these less frequent words when they appear in a training context. And this gap, this memorization, is what enable us for effective auditing. However, this gap is not captured by test accuracy at all because 90% of data are from the top 20% of words where we don't such a gap. We don't see such a gap. And in other words, what it means is you only need to do very well on these most frequent words in order to achieve a high test accuracy. Next thing we did is a countermeasure for this memorization problem. And we did that through differential privacy. And to simply put, differential privacy tries to learn useful information about a population while learn nothing about an individual. So by design, differential privacy should prevent the model memorizing any training data point. And here is the same plot for a differentially private language model trained on Reddit dataset. And from this plot, you can see that there is indeed no more memorization anymore. The blue curve and the red curve almost overlaps exactly, which means the model is behaving exactly the same on training and unseen context. Auditing, of course, failed in this case because we can no longer difference between models training and unseen data from its output. But you can also see that the model never predicts real words. The predicted rank for the real words are all pretty low. And then it's very hard to argue what's the actual utility of this model. And here are the takeaways for this work. We demonstrate that text generation models can memorize their training text by assigning much higher rank to real words when they appear in a training context. And this memorization enables us for effective auditing of data provenance and thus detecting unauthorized data collection. In the next part of this talk, I want to tell you more about one of our most recent work. These are the adversarial inputs for NLP models, and we call these adversarial semantic collisions. And the scenario is at test time, adversary controls the input and tries to trick the model to make unexpected predictions. In this work, we focused on these models for computing semantic similarities. These models can usually take a pair of text as input and output a single score for measuring to tell if these two texts are semantically similar or relevant. And these type of models have wide applications in many services. For example, in retrieval systems, where the input is a user search query, and then we can use these models to compute a similarity score between this query and all possible candidate documents in the database, and then rank these documents based on the similarity scores, and finally return users the most relevant documents. And similarly, these models can also be used for applications like Smart Reply, where the input is a user email or a text messages, and we can use this model again to compute the similarity scores between this input and all the candidate responses, and then display users the most relevant responses from the similarity scores. Platforms like Quora can also use these models for merging semantically equivalent content. And if these models are working as expected, then given a user input and its most related candidate in the database, the model should output a very high similarity score so that these candidates can be ranked as top. In this work, however, we show that it is possible to have certain text which is semantically unrelated to the user input, yet the model will assign a very high score to these unrelated text. And we call these text semantic collisions. And effectively, these collisions will become the most relevant answer. And these collisions can have real security concerns. Let's imagine an adversary who can generate these collisions for certain user inputs, and then insert these collisions into the set of all possible candidates. And then when the model sees the attacked user inputs again, it will assign a very high similarity score to these collisions, and these collisions will be the candidates that's retrieved and returned to the users. And furthermore, we also show that it is possible to inject certain payload message into these collisions, and the model will then, such as the payload here, for example, can be the spam messages showing the red here, and the model will then display these spam messages back to the user. I also want to point out that the semantic collisions are not the same as traditional adversarial examples. In adversarial examples, you typically apply certain imperceptible perturbation to your inputs so that the semantics of your input remains the same, yet the model flips its predictions. In the case of semantic collisions, we are generating a collision with a different semantics to the input, yet the model will think these collisions has similar semantics to the input. Now let's talk about how we can actually generate these collisions. We first consider generate collisions without any constraint, and we call these aggressive collisions. And we formulate an optimization problem for the generating process, where the objective here is to maximize the model similarity score for target input X and the collision C. And we can perform this optimization in two steps. In step one, we optimize for a relaxed version of the collision in the continuous space with gradient-based methods. So we can feed the model with the input X and the relaxed collision, compute their similarity score, and use backpropagation to compute the gradients for the relaxed collision, and then update the relaxed collision with its gradients to maximize the score. And once we find these optimal relaxed collisions, we can convert it back to discrete space using a beam search. And now let's look at some examples for these aggressive collisions. And here is an examples of collisions for a retrieval system. The collisions is shown in the red here, and you can see that it is ranked as the top relevant candidate for that given search query input. The actual related content are shown in the blue here, but their similarity scores are not as high as the collision. And here is an example of collisions for response suggestion models. And you can see the collision in the red here is retrieved as the most relevant response for a given user input dialog. Here is another example of collisions that is identified as a paraphrase for a given input sentence with very high confidence. And these aggressive collisions, they are very effective. However, there is one issue in these collisions. That is, they are nonsense. And it is likely that we can filter this collision out because their perplexity scores are higher than other candidates. And now I'll show you how we can evade such filtering and reduce the perplexity of collisions. And we can do that by incorporating a language model. So we modify the optimization objective to be the interpolation between the similarity score and the language model likelihood term computed on the collision. And we propose two approaches for optimizing this objective. First one is what we call regularized collisions, where we optimize with a relaxed version of the language model likelihood term. And here is an example for the regularized collisions. And you can see the collision in the red here is still nonsense. However, its perplexity score on the language model is actually much lower. Another approach for optimizing the objective is what we call natural collisions, where we modify a language model decoding step with a joint beam search on both the similarity score and the language model likelihood term, so that the language model can generate colliding and fluent word at the same time. And here is an example of a natural collisions. This collision is shown in the red here. And you can see that this sentence is actually much more fluent compared to the other ones. And when we insert this collision into this article here, the model will extract this collision as its summary, even though this content is not related to the content of the article at all. And here is our experimental setup for the semantic collisions. We considered 4 tasks, including paraphrase identification, document retrieval, response suggestion, and extractive summarization. We used benchmark data sets for these tasks and also the state-of-the-art models that are all based on transformers. And here is our results. We report the similarity score output by the model computed on the input and their collisions. We also compare the scores of collisions to the most relevant candidate in the dataset, the ground truth. So in the black dashed line here, we show the similarity scores computed on the ground truth for the input. And in the blue, green, and red bars, we show the similarity scores computed on aggressive, regularized, and natural collisions, respectively. And from this plot, you can see that the blue bars, they are always higher than the scores of ground truth for all datasets, which means the aggressive collisions are really effective. They can always be retrieved as almost always be retrieved as the top relevant candidate. For the natural and regularized collisions, you can see their similarity score are lower than the aggressive ones, but sometimes they can also be higher than the scores of ground truth. And even though their score is not as high, their rank among all possible candidates can also be high. And finally, I want to show you the perplexity scores of these collisions. And here are the histograms of perplexity computed on these collisions and real data from a language model. And the perplexity for real data are shown in the gray histograms. The blue, green, and the red bars shows the perplexities for aggressive, regularized, and natural collisions. From this plot, you can see that there's a gap between the blue bars and the rest, which means it is likely that you can filter these aggressive collisions out based on the perplexities. However, you can also see that the regularized and natural collisions, their perplexity scores can overlap with the real data a lot, and filter those collisions out will likely result in a lot of false positives and thus hurt the model's utility score. And here are the takeaways for this work. We have demonstrated that given an input, we can generate an unrelated text, a collision, that fool the NLP models into thinking the collision and the input are semantically similar. We also show that simple perplexity-based filtering is not enough to prevent such collisions. I have talked about the threads we have worked on for machine learning systems. However, these threads are by no means a comprehensive coverage of all the threads you can have to ML. And I'll briefly describe other threads to machine learning in these slides. You can have threats to a model's confidentiality. A deployed model can be stolen or misused by an adversary. In this case, the question we want to ask is, can we detect this IP infringement? How can we protect models' copyright? There are threats to models' availability as well. Adversary can generate certain input to slow down model's decision-making process or even increase the energy consumption of model prediction time. There are other compliance issues. For example, how do these models comply with the right to be forgotten? A user can request their data to be removed from the server, and perhaps removing a data from the database is quite easy, but how do I know if my information was removed from a trained machine learning model? I think all these problems are very interesting research topics for future directions. All right, to conclude, I hope you can see from this from this talk that test accuracy is really not enough as the deciding metric for model deployment because it only measures if the model learned well on its given task. When we train and develop new models or even just designing new learning algorithms, we really need to take all aspects into consideration. I also want to make the point that attacks are not only attacks. Attacks can provide lower bound measurements of the threats. Attacks can also help us better understand the issues we can have to ML and potentially provide insights for better defense. Attacks can also be used positively, as we've seen in the case of using memorization for building auditing techniques and detect unauthorized data collection. And here is a summary of all the publications that are related to this thesis. And I have highlighted the papers where I am the main author. Okay, so this is the week of Thanksgiving, and I also want to express my gratitude and appreciation. And first and foremost, to my committee members, I want to say I'm extremely lucky to have Vitaly as my advisor. I probably overlearned from him as a PhD student as well, in a good sense. And he taught me how to identify and formulate research problems, how to write papers and present them to people, how to succeed in academia or even in life. He's the best advisor one can possibly have, and he's the kind of researcher I wanted to be in the future. I want to thank Tom, who introduced me to security and privacy problems in machine learning when I first came to Cornell Tech. And I have worked on this topic for my entire PhD, while Tom seems to have quit this area. I also want to thank Helen and her awesome, wonderful digital life initiative. They're the people who actually cared about how technology impact people's privacy and the quality of life. I learned a lot about the societal impact aspect of the technology and also how people outside our field view our work from a different perspective, which is a truly valuable experience for me. I want to thank my co-authors. They are incredible researchers in this field, and without their help, I wouldn't be able to complete this thesis and give this talk. I want to thank all my friends here at Cornell and New York City. Their support and encouragement made my PhD experience less painful. And I haven't been home for like 3 years, and their companion made me feel less homesick. I also want to thank my mentors and colleagues at Amazon, Google, and Petrium during my internships. I learned a lot about how security privacy research is deployed in practice, and also about the difference between academia research and the real world. And finally, I want to thank my parents for their endless support for my entire life and letting me do whatever I wanted to do, which is actually very uncommon for Asian parents. And finally, I want to thank my girlfriend, Victoria. She has helped me in any way she can, and I really appreciate her patience and willingness to listen when I had a hard time, even though she knows nothing about computer science. And thank you everyone for coming and listening to my talk. I'm happy to take any questions you might have.